of each of them. Okay, read the question on the screen. A disk of mass m and radius r is given an impulse which imparts velocity v naught to its center of mass tangential to the wall of room, and the initial angular velocity is 0. Given that v naught and mu 0.5 between what? Between the disk and the inner wall. Inner wall rough, fixed room. Okay, can you now hear me clearly?
Yes, sir.
Yes.
Okay, that one, yeah. No, it will be like this, no? So this will be inner wall is rough, outer wall, that one. There's not a ring room. So what is the best thing? You take your some plate, circular shaped plate, and you take the carom board striker or coin or lid, some bottle, any lid, that you keep it like this and just give some velocity, it will start moving like this, along the circumference. Please do understand the first situation. See, problem solving, okay, we'll do. What is there in that one? First, what is the question you have to understand, no? So this will be some sort of a lid. If you give that, it will move where? It will move along the circumference, no? For some distance. Because why? Because this surface bottom will be rough, but he's telling this is smooth. I think I can best help you with a diagram. Inner wall, outer wall, both will come. So this is the let's get into the radius of this is given capital R. At least all of you. So this is the inner wall. This is smooth. There's no problem. This surface is, and we have center C. Let this be O. Let's assume these things. Or I'll write this. This is O. Center of the room. There's the outer wall of room. This rough, and this is smooth. This radius is R. Let's get into, and it's a fixed, no? This room is fixed. When you give velocity, what will happen to it? When you give velocity, so this will be in contact with this. How the weight mg will act into the plane of paper? There's a plate. There's a lid. As a teacher, I do have limitations. I cannot show more than this. Please do understand now. No. Okay, let's get into it. So it'll be in contact with the inner wall, no? So there'll be a normal contact. Show that normal contact. This is a T code 0. Normal contact with that. So initial velocity how much given? V naught. After some time, the disk will be here. It will have velocity v. It will be tangential to the inner wall, that one. So this will be radius r. Tell me what are things. So it will initially it will have normal contact n naught, no? At any instant of time, it will have normal contact n. How the friction should act? Friction should act in this direction. Why? This friction acting will set up a torque alpha. So because of that, angular velocity will be there. I'll show omega here. This is alpha. And it will deter the motion of center of mass. You see. So what happened to velocity of the disk will keep on decreasing because of friction. At the same time, the friction will set up a torque about center C, and it will set up a torque because of that angular velocity keep on increases. So what is the question? The time at which disk starts pure rolling. I think once you get this, rest of everything you can find out. Smooth floor. This is a smooth floor. Get into the problem. So what is n? And at any instant of time, let me go for it. So what is the normal reaction provided by it? N is equal to this diagram. I'll shift it here. You can try in your home. Oh, I'll do later on adjustment. Where it is gone? Yeah. Let's come forward. So what is n is equal to? N is equal to mv square by r minus r. The distance OC is equal to r minus r. Then the friction is what? Will deter the motion of center of mass. F equal to minus m dv by dt. What is F? F should be equal to mu n. Mu n equal to minus m dv by dt. So this should be equal to, so mu mv square r minus r m dv by dt. So let's solve for v. So this will be v square dv. So like I'll bring everything on this side. Mu r minus r dt, negative sign, let it be here, and this will be v to power of minus 2 dv v naught v limit 0 to t. Negative sign, so v minus, so this will become mu t. This negative sign, I'll keep it for this. Let it be. No. So I'll proceed with the calculations. Let me write everything in one page so that it will be easy for you to follow. This negative of this minus 1 by v. After integrating, substituting limit. So solving this, I'll get expression for v as v naught r minus r by this is the expression for the speed of the disk at any instant of time t. Call this equation 1. I think you saw rest all everything. You have to just get into the calculation. Now let's come to the rotative motion. The friction acting here. So from where the friction will come, because the surface between the inner wall and the disk is rough, no? Here. So it is what initially it will slip, no? This is at t equals 0, what we did, and this is at any time t. So at any time t, the disk will be here. At any time t, we are discussing. So what is the speed of the disk at any time t? We got this. Similarly, I want that omega, which I shown. So how to bring that omega? I know friction, the torque acting, F into R about center of mass is equal to moment of inertia, IC into alpha. What is F? F is equal to again mu n. What is moment of inertia? Mr square by 2 alpha. It's a disk mass m and radius r. So let's substitute the value of n. This is equal to mu But we have V and alpha, no? What to do? Alpha, can you write it as d omega by dt? Alpha, let it be d omega by dt. So this will become everything. Then one more thing. This mu v square by r minus r. What you can write it as? Mu m v square r minus m dv by dt. Please correlate. So this equation, I'll give name like this. One, let it be like this. So that will be easy for you. Put 1 in 3. When you put 1 in 3, so in place of mu m v square r minus r, what you can write it as? Mu m v square r minus r. So can we write it as m dv by dt? And some method is what? And just applied it here. If you want, you can solve. Just to minimize calculations, I just proceeded in this way. After this, what shall we do? FR, sorry. F smaller. Okay, yeah, thank you. So M get cancels, dt get cancels. So you can see the problem has become very simple. This will be r minus r dv by dt, f into r. Okay, one r is there, no, here. I think I missed r. I'll write it r here. So this will be r. One r get cancelled. So dv is equal to r by 2 d omega. No, integrate. Initially, this is v naught. This is omega. At t equals 0, what was it? It was given only linear velocity, no? After some time t, it will have both linear as well as angular velocity. When linear velocity is v, what is the angular velocity? Is omega. So solving this will end up with v naught minus v is equal to r omega by 2. Call equation 4. For pure rolling, after some time it will attain pure rolling. Though friction is there, I think already we are done. Just we are discussing friction on curved surface, rolling on curved surface here. So once it attains pure rolling, I think I can't minimize more than this. Yeah. When it attains pure rolling, at pure rolling, what is the basic condition? V equal to r omega. What is V? So we know V naught plus r omega 2. At pure rolling, V equal to r omega is there. So shall we use these equations only? In place of r omega, I'll write this equation. So call, let me phi. Put phi in 4. So when you put phi in 4, we get V naught minus V. R omega is V. So therefore, what is V is equal to 2 V naught by 3. When it attains pure rolling, it will have that much of linear velocity. Now we know V. That value of V you substitute here, you'll get the omega. Okay, now let's get into the problem. It's asking first the time, no? What to do, from where the time? This value of V, you have to substitute in equation 4, 5, 6. Put 6 in 2, solve for V, you write it as 2 V naught by 3. Solve for T, you'll get the required time. I'll scroll down. Now put 6 into. So 2 V naught by 3 is equal to V naught R minus R. Solve for T. I'll write it directly. Huh? This is a time. Huh? Is there it's there in Pathfinder. Pathfinder just here some small idea. I just made it as like some good problem. Nothing that one. The Pathfinder only is asking the x coordinate. Directly I brought the pure rolling condition. So if the surface is curved, no, so you can apply this method. Time taken to attain pure rolling. So once you know time, I think all the things we can, the speed of center of mass of the disk when it attains pure rolling. Already we know V naught is given, so you'll get the V. The angular velocity of the disk. Don't go for again. So substitute here only. You know R omega. You know V and R. Equation 5. Substitute will get omega. Normal force acting on the disk when it starts pure rolling. What to do in that case? When it ends pure rolling, so substitute the value of V here. M you know R. You'll get the normal contact. Can you work out? Just to say, these ideas are very important. Equation, the first initial set of equations, these are very important. The normal contact, the centripetal force is what normal contact. Will I agree? I think I started the data like this. The normal force will provide required centripetal force. You can see here. Since and it depends on linear velocity, the linear velocity changes, so normal contact also changes. Proportion means here you have to ask question, sir, friction is it a constant or variable? Friction depends on what? Mu n. N is variable. Let it be, no problem. So can we apply conservation of mechanism? No. Net work done by friction will not be zero. You check the final kinetic energy will be less than initial kinetic energy. So whatever the friction does work. And these are some additional things. Net work done by friction is non-zero. Sir, how do you can say this? Look at the final kinetic energy. It will be less than initial kinetic energy. So you can expect in advance questions of this kind. I'll scroll down.